So welcome everyone to this Wednesday seminar that will be given a presentation by Alasdair Skelton. My name is Paul Glantz. I will taking care of the host work here today. And Alasdair has been is the chairman of Researcher Desk for a couple of years back in time. He has also been co-director of Berlin Center for Climate Research during 8 years, have built up a lot of knowledge about the climate change and climate crisis. So today he will talk, his title today is to reflect on the meaning of time amidst the climate crisis. So please, Alasdair, the floor is yours.
Thank you very much, Paul. I'm just like a confirmation that you can see my pictures and that I can be heard. Is that
yes,
what?
yes, we can hear you.
Thank you very much. Thank you for coming. I'm going to spend around about 20 minutes or so reflecting on the meaning of time. I'm firmly of the opinion that we struggle to understand what time is and what time is in terms of the climate crisis. I think if we do understand time a little bit better, we will understand the immediacy of the crisis that's happening all around us, and we will be better equipped to act. I'm hoping that this will be a presentation that gives hope and not just darkness, and I will do my best. And I want to begin here. This is a view from a beach in southern Sweden, in Skåne, and it's early evening. And when I'm standing there, I'm looking at the moon. Except for I'm not really. You see, what I'm really looking at is what the moon looked like 1 second before the moment when I am looking. And that's because the moon is so far away, it takes 1 second for the light reflected from the sun off the moon to reach the earth. So I'm looking at what the moon looked like 1 second ago. This is the same beach in the morning. And here I'm looking at the sun. But again, I'm not really looking at the sun. I'm looking at what the sun looked like 8 minutes ago, 8 minutes before when I'm standing there. Now, 8 minutes ago, you were probably trying to find the link to Researcher's Desk to come in and join us. Already a perceivable amount of time. If we look further afield to our nearest group of stars, Alpha Centauri, we're not seeing Alpha Centauri at all, how it looks. Not right now, we're seeing what it looked like 4 years ago. Now I want you to take a moment to remember what the world was like 4 years ago. That was before the coronavirus pandemic. That was before the war in Ukraine. It was a very different world. Yet when you're looking at Alpha Centauri, you're looking at what it looked like back then. We can go further. You'll need a telescope now, but with a telescope, we can see the Andromeda galaxy. It's not quite our nearest galaxy, but almost. But what you're looking at is not the galaxy itself. What you're looking at is what it looked like 2.6 million years ago. That was at the start of the time geologists call the Ice Age, a time in which glaciers advance over the northern and southern hemisphere periodically in rhythm with the Earth's orbital variations. We can look far, far further. With the help of a technique called gravitational lensing, it's possible and the use of the most powerful telescopes on Earth, it's possible to see Earendel. Now, what you're looking at when you're looking at Earendel is a star, what that star looked like 12.9 billion years ago. 12.9 billion years And when we think about that for a moment, knowing that the lifetime of a star is something between 10 and 15 billion years, you can ask yourself the question, is Earandel there at all? Or are you seeing back in time to something that no longer exists? This is the immensity of time. And this is the framework of geological time that we need to think about when we're thinking about the climate crisis. So let's just map that out. The Big Bang, 13.8 billion years ago. Just a little bit before the time we were looking at when we were looking at Earandel. The birth of the Earth, 4.6 billion years ago, and today. We probably lost the ability to conceive of geological time when we were around about 9 years old and we left the age of fantasy behind us. As adults, what we can do is we can use analogies to try and help us grasp what we mean by such immense periods of time. And I'll do that now, and I hope it will help. What I'm going to do is I'm going to take a 24-hour period. I'm going to start the clock at midnight on the first day, at the birth of the Earth. And by midnight on the second day, we've reached today. So let us walk through the history of the Earth and set ourselves and the climate crisis in that perspective. I'm not going to begin with the absolute oldest rocks in the world, not even in Europe, but almost the oldest in Europe. And I'm going to begin with them because they're beneath Sapmi, and that means something to us. And it makes it local. This is the world that geologists can envisage beneath the moorlands of Sapmi. 100,000 tiny continents, each one of them probably no bigger than Greater Stockholm, moving rapidly around the Earth, crashing with one another, bouncing back in a very, very hot world. This is 2.8 billion years ago. This is 12 minutes past 9 in the morning. We've already slept the night and woken on this one geological day. Now, those tiny little continents move swiftly around the world and collide with one another. And stage by stage, they amalgamate into larger continents, and the world becomes more like what we think of it today. A lot happens. 2.5 billion years ago, we see the rise of oxygen. There was a time when there was no oxygen in the atmosphere. It was a very different kind of life that existed then. This was actually the first environmental catastrophe. The very creatures that created the oxygen died because of it. It's 1048. We're already almost halfway through the history of the Earth. The structures which my student Suzanne has so elegantly drawn in the foreground are called stromatolites. Stromatolites are important. Stromatolites are fossils made by colonies of cyanobacteria. They're the first fossilized forms of life. They've been on, we find them back 3.5 billion years of Earth history. But they are records of life that was before. It's hard to envisage it when you just see a lump of rock sitting in the water. But those layers are layers and layers of colonies of living things. Now, the existence of life so long ago creates a paradox. And that paradox can be spelled out as follows. You see, the sun was fainter back then. So if the sun was fainter, the Earth should have been colder. In fact, frozen over entirely. How can there possibly have existed life? This is one of the great paradoxes of our time. And when I say our time, I mean our 4.6 billion years. The person who first solved this paradox is Svante Arrhenius. In 1896, the Swedish chemist put forward a solution to the paradox. What Arrhenius said was that it had to do with the formation of limestone by the weathering of rocks. What a cryptic thing to say. What could he possibly mean? How could that be the solution to the paradox of how life could exist for 3.5 billion years on the planet? The formation of limestone by the weathering of rocks. How do you make a rock by weathering a rock? None of it makes an awful lot of sense, really, does it? Let's dig into his paradox, to Arrhenius' solution, the formation of limestone by the weathering of rocks. Well, as a rock, there's all sorts of them, but let's just take a normal rock that we feel familiar with in Sweden, a granite. And a limestone, we probably feel familiar with them too. A walk on the shores of Gotland will remind us what they look like, all full of shells. So what do we mean by the formation of limestone by the weathering of rocks? Well, as rocks weather, they remove CO2 from the air. They remove carbon dioxide from the air. The mechanism is not so important to delve into here. You can trust me that they do. As they weather away and turn to clay, they remove CO2 from the air. The CO2 ends up in the water where, after a long, long time, it will react with other elements and turn into limestone. And that limestone will sit there for a very, very, very long time until at some point it melts into a magma and gets carried to the base of a volcano where it's erupted again. And as it's erupted, that carbon dioxide is returned to the atmosphere. This is the formation of limestone by the weathering of rocks. So how does it work? What does it actually do? Well, let's imagine that the sun was once faint and becomes brighter. Well, that should make it warmer. But if it's warmer, that reaction whereby rocks weather and turn to clay will be faster. And if that reaction's faster, carbon dioxide is sucked out of the air. And if carbon dioxide is sucked out of the air, the temperature will go down again. And thereby, this very, very simple reaction has stabilized the climate of planet Earth for 3.5 billion years. Let's return to our story. All those little continents beneath Sapmi have crashed into one another and formed just one single continent that crosses the center of the Earth, crosses the equator. That continent we will call Nuna. You might recognize small parts of it. Maybe you see Baltica turned on its side, maybe North America, maybe you don't. Maybe you can grasp pieces of Australia. I don't know. By the time this continent formed, it's 2:30 in the afternoon. It's past the time of the seminar that you're now listening to. We're mid-afternoon. And then something strange happens. With that continent sitting stably on the equator, we enter a time which geologists call the boring billion. 1 billion years where we simply don't know what happened. There are almost no rocks. Was it boring? Was it nothing that happened? Or is it that we just don't know? I don't know. It could be either. But we came out of the boring billion 1 billion years later, and the world looked roughly the same. The supercontinent had a slightly different name. It's called Rodinia now. It's 800 million years ago. Maybe you'll recognize various parts. You might see Baltica again. You might see North America, perhaps India, perhaps Australia. But they're all joined together, one continent across the world, with a great big mountain chain across its middle. It's evening now. It's 7:45 in the evening. And various things happen, and a bunch of geological consequences, and the Earth cools more than it has done, to the best of our knowledge, throughout Earth's history. And Earth plunges into a snowball state 716 million years ago at 8:15 in the evening. And that lasts for a very long time. But ultimately, volcanoes pump carbon dioxide into the atmosphere, and it ends 635 million years ago at 20 to 9 in the evening. And this sets the stage for the explosion of life, which happened 541 million years ago and created all those fossils you know and love, and you probably have one or two of them on your mantelpiece. It's 9:10 in the evening. And life was not just in the sea, then it occupied the land, both as animals and also as vegetation. And that vegetation died. And when that vegetation died, it turned into coal. And the coal started to accumulate. And it started to accumulate 359 million years ago, 6 minutes past 10 in the evening, or just 2 hours left on our geological day. And coal has continued to accumulate ever since then. And then the age of the dinosaurs began, 228 million years ago, on yet another supercontinent, the supercontinent Pangaea. It's 10 to 11 in the evening. But even that time was not going to go on forever, because the age of the dinosaurs also came to an end 66 million years ago with the fifth mass extinction. It's now 20 to midnight. The sixth mass extinction is recorded in this dark layer of rock between two whitish rocks, both teeming with life. That dark layer of rock contains an odd element, iridium, that can only be of extraterrestrial origin, telling of a meteorite that struck down on the planet and abolished most of life on Earth, the fifth mass extinction. And then, 50 million years ago, the Himalaya were born. India and Asia collided. It's quarter to midnight now. But as the Himalaya were born, great mountains raised skywards, and they exposed masses of fresh rock to weathering. And that took carbon dioxide out of the air. So the Earth cooled. And glaciers formed in Antarctica 35 million years ago at 11 minutes to midnight. And the Arctic Ocean froze over 2.6 million years ago at 1 minute to midnight. And this marks the beginning of the Ice Age. Remember Andromeda. This is the same time as we see when we look at Andromeda. And then let's delve deeper into that last minute. There comes the rise of humans. 6 seconds before midnight, a species that attempts to dominate over nature in a very dangerous way. And the human separates itself from nature, and as separated from nature, it can see nature as a resource, and it consumes and the human consumes the green parts of the earth and then turns underground in search of energy, in search of power, and the Industrial Revolution begins. And the Industrial Revolution begins just 5 milliseconds before midnight on our geological day. The image here shows mining in southern Sweden, in the small village of Nyholm in Skåne, where 7 million tons of coal were once mined. And the Industrial Revolution also affects this cycle, because the Industrial Revolution is powered by fossil fuels. And when we burn them, we play at being volcanoes. And we add masses more carbon dioxide to the air, so the temperature rises. And so is the origin of the climate crisis, which began 1 millisecond before midnight on our geological day. 1 millisecond before midnight. And it's so difficult to appreciate its immediacy, that millisecond matters so much, but it does. So I take you to this view where you see a man standing on a beach, looking out over the sea, holding sandals, standing barefoot in the sand. What you don't see is the family to the right, with the father and his children running in the sand. You don't see them because I haven't shown them to you deliberately. What you don't necessarily realize straight away is the picture is all wrong. The rocks in the foreground should not be visible. But the man there is on holiday and doesn't really know that that matters. Nor does the father with his children, just thinks it's the tide. What you don't know is that line on the horizon is a tsunami wave moving towards you. Because the picture was taken at 10:27 on the 26th of December 2004 in Khao Lak, Thailand. 3 minutes later, that wave will wash over the beach and 4,000 people will die. Why did people stand and watch in those fatal last 3 minutes? Because they had no impression of scale. These are our 3 minutes. For us, it is not a tsunami, it is the climate crisis. The water is receded from the shore, or more correctly said, the sea is rising. And there are the heat waves. There are the forest fires. All the signals are there. Yet we cannot see its scale, so we do not run. These are our 3 minutes. Or if we're going to think in our day, this is our millisecond. We must use them wisely. So is there hope for a planet, from a species that can view its very home from another celestial body? Is there hope for this planet? Is there hope for humanity? Is there hope for nature? I think so. And I will leave you with the oak trees of Visingö, because herein lies the recipe of hope. You may or may not have been there, but these oak trees are very, very spectacular. They're very, very tall and very, very straight. Surrounding them are beech trees, and beech trees shade out the light. So the oak trees must go quickly and straight to capture the light and photosynthesize. The oak trees were planted in 1831 on the island of Visingö, in the Lake Vättern, which is the second largest lake in Sweden. Why were they planted? They were planted for the purpose of building ships. And when harvest time came in the 1970s, they were no longer needed because ships were made of metal. So they are allowed to stand still to this day. Why do I show you this? Well, there are lessons to be learned from the oak trees of Visingö. When you look into the future, it can look very, very dark. But as for the people who planted these oak trees, there is a lesson here. When we look to the future, we should expect the unexpected. Ships will be made of metal, not wood. Humans will respond in ways that we do not see as imaginable. And we can learn another lesson from the oak trees. Imagine you are now the person who planted this oak tree. You know what you're doing when you plant an oak tree. You know it will grow, it will not reach its full height. It will not be ready for harvest until long after you are gone. But you plant it anyhow. You plant it for a future. And this is what it means to take on the climate crisis. We are planting an oak tree. And we often say it is for our children, and to some extent it is, but it's for much further into the future than that. We're planting an oak tree for generations that have not been born yet. We're planting an oak tree for species that have not been born yet, animals, plants, and everything, all the living things on this planet. Thank you.
Thank you so much, Alasdair.